Alright, given that f of x is equal to x squared plus 2x minus 3 and g of x is equal to x plus 5, determine the intervals of increase and decrease of h of x in each case, where h of x is equal to f of x minus g of x plus 2. Okay, so if we're looking at, first what we want to do here is figure out what h of x will look like. So we're going to take f of x, so x squared plus 2x minus 3, and then we're going to subtract it by g of x, which is x plus 5. Then we're going to add 2 to the outside. So h of x here is going to give us x squared plus 2x minus 3 minus x minus 5. So you have to carry the negative and expand outwards, plus 2. So in this case, h of x is equal to, if I collect the like terms, we get x squared plus 2x minus x plus x minus 3 minus 5 is negative 8 plus 2 is negative 6. Okay, so h of x is x squared plus x minus 6. Okay, so now we have h of x. What you want to do is find the derivative function. Okay, and the reason we want to find the derivative function is because we want to isolate the critical numbers, also known as critical points. So the critical numbers will occur when h prime of x, or the first derivative function, is equal to 0. So if we find our first derivative function and find the derivative of this, right, you're going to use the combination of the sum and product rule of differentiation, and I'm going to do the derivative of x squared plus x minus 6, which is basically 2x plus 1. Okay, so now that I have my derivative function, I'm going to let the derivative function equal 0. Okay, so if I let my derivative function equal 0, I get 2x plus 1 is equal to 0. I'm going to move the 1 to the other side. 2x is equal to negative 1. If you want to solve for x, you divide by 2 to 2x, and whenever I do this side, I do this side. So x is equal to negative 1/2. Okay, so this is the x value in which you basically get a critical point, right? To find the y value, you're going to plug this back into your original function. So you plug this into your h of x function. So you do h of negative 1/2 is equal to negative 1/2 squared plus negative 1/2 minus 6, which is equal to 1/4 minus 1/2 minus 6, which is 1/4 minus 2/4 minus, I'm going to change the 6 by multiplying by 4, 24 over 4. So you get negative 1 minus 24, which is negative 25 over 4. Okay, so h of negative 1/2 is negative 25 over 4. So now that we have the point, right, using this critical number of x, what you want to do is you want to find the intervals of increase and decrease. So to find the interval of increase and decrease, we know that an interval of increase will occur when the first derivative function, in this case h prime of x, should be greater than 0. We know that an interval of decrease function, h prime of x, conversely should be less than 0. Okay, we have our derivative function, right? We have the derivative function h prime of x, which is equal to 2x plus 1. If we're basically solving for when it's greater than 0, right, 2x, we set h prime of x greater than 0, so 2x plus 1 is greater than 0. Then 2x here would be greater than negative 1, and then x would be greater than negative 1/2. You divide 2 to both sides. Okay, so this is an interval of increase. Okay. The next thing you want to do here is, we know what our critical point is. At a critical point of negative 1/2 and negative 25 over 4, we have some kind of extrema. An extrema occurs when you have a maximum or minimum point, right? A critical number will indicate an extrema, but it can also indicate asymptotes, like a vertical asymptote, for instance. Now, in this case, we want to figure out the interval of decrease. So for an interval of decrease, we let h prime of x be less than 0, so we do 2x plus 1 is less than 0, 2x is less than negative 1, x is less than negative 1/2. Okay, so therefore we have an interval of decrease at, and if x is less than negative 1/2, you can write this as negative infinity and negative 1/2, and there's an interval of increase at x belongs to negative 1/2 and positive infinity. Okay, so that's how you look at intervals of increase and decrease by assessing the derivative function.